And this is 31 minutes past the hour. So we're gonna start our class today. Hi everyone, welcome and welcome back for people who have been following. This is our 14th session at Hackaday, and also 6 sessions ago we started doing more coding. For anyone who's joining for the first time, you can find all the past materials in the Hackaday project. Every Sunday we do this class, except last week we were on vacation. Every week we do 30 minutes to 1 hour discussing a topic. The classes are recorded and is also using my comics. Every week I will post something new on the project. We are also using the Microsoft Q# documentation for our sample code, for our conceptual reading. You can also feel free to use that for your own understanding. We have been using the quantum katas for coding, which is a very nice tool for hands-on guide of a concept. You can build up your Q# skill using these tutorials. So for today, we're going to go back to look at the entanglement. So we're gonna do one more example that uses entanglement in our algorithm, and to see how that is helpful. We have discussed previously the basic concepts like superposition and interference and entanglement. These 3 things are the most important concepts for quantum computing. We also discussed teleportation and superdense coding. Those are both examples using entanglement in the algorithm, and it helps you see how we can use entanglement to help do some tasks. And linear algebra is needed for quantum computing, but it's not very difficult. It's linear, so it's not gonna get that hard. And the Q# is a very good high-level tool for you to get more understanding and be able to eventually build your own algorithm using this quantum-focused language. So let's take a few steps back just to revise important things about entanglement. Entanglement is a result of superposition, and superposition is the fundamental reason why quantum computing could work, and is also fundamental to how our universe is being built. It's fundamentally quantum mechanical. So say you have 2 qubits, you would be able to have these 4 different types of configurations. Just using these colors as zeros and ones. So these could be 2 zeros, these could be 2 ones, and we also could have 1 0 and 1 1 and 1 and the other way around. And because we can enable superposition in a quantum system, then we are able to put any of these combinations in superposition. So we can build these special states called Bell states. And actually, in this case, is not necessarily Bell states, because A and these amplitudes, A, D, B, C, can be arbitrary. You can build a situation that has a first qubit in 0 and second qubit in 0, with the superposition that first qubit is 1 and second qubit is 1. Or you can build a case that you have first qubit is 0 and second qubit is 1, with a superposition of first qubit being 1 and second qubit being 0. If you have equal amplitudes for these states, then you can form a special state called Bell state. So Bell state, we have 4 options. All 4 methods, all 4 configurations can be a Bell state. And what's special about them is that they have equal amplitudes, and which means they have equal probability of getting these states out. And entanglement means that when you measure one of the qubits, you don't even have to measure your another qubit to know what it is because of the setup for Bell states. So say if you are in a state like this one, 0, 0 plus 1, 1, you can have, if you measure your first qubit be 0, then you know there's no way that your second qubit will be in 1 because this state is what's contributing to it. So you would know that you would measure the second qubit being 0 with the probability of 1/2. Equally, if your first qubit is 1, you would know your second qubit is 1. So this is what entanglement is. You know that your two qubits are correlated. The results are correlated. If people don't mind, you should mute yourselves. Let me also check. I can do that here too. Yeah, thank you. So today we're going to talk about a game called Chsh Game. This stands for two people's initials. Those are four physicists who came up with the schema. And it was part of a proof of the Bell's theorem. So for anyone who's interested in the history, you should look it up on the history of the development of this CHSH experiment. And it also is a way that they're trying to prove entanglement is not a property that needs a local hidden variable. So because when people first discovered entanglements or set it up, they thought that, oh, this is strange. If I split two entangled qubits, I can measure one and know the other one as if there's some communication in between these two qubits. And they thought that there might be some hidden variable that they cannot see, and that's local, and they can determine a qubit that's infinite far away. But then a lot of proofs has shown that is actually entanglement is not relying on hidden variables, local hidden variables. So it goes back to something very fundamental, but it's also really fun to look at this game and the algorithm because it is showing the specific case that it could be better than a classical game strategy. So the setup looks like this. Alice and Bob, they are playing this game, and the rule of the game is that they would be separated physically, and they can't communicate in any way, but they have to kind of guess what bit or information or card they should show. They have a referee who has two cards. The L he will show to Alice, and M he will show to Bob. But he would not be sharing M to Alice, so Alice wouldn't know what Bob gets. So depends on the information on L and M, Alice and Bob can give a guess and output their A and B. If L times M equals to A control B, then they can win the game. Otherwise, is loss. So if you set up the truth table for this, you will have 0, 0, 0, 1, 1, 0, 1, 1 for L and M. And then you can calculate what L times M equals to 0, 0, 0, 1. So if A control B gives exactly this, or so each time they can do this game many times. So each time they guess it correctly, they will be winning. So you will see that actually classically they can do, say, because it's more likely to get 0. Then they can say, why don't we just always give out zeros? So like in this case, and we can at least get 70% chance of winning. You can actually do better if you have a pair of qubits. If this is allowed as a quantum game, you can actually improve that chance of winning. So also, you can also understand that in order to get 0001, your A and B has to be 0011 for the case of 000, because you can calculate what A control B would be. So 0 control 0 will still be 0. 1 control 1 would flip this, because your 1 is the control bit and your B is the target bit, so it flips to 0. So these two cases will give you these three cases. But then it gets harder when your L and M is both are 1s. So then Alice has to have a 0 when Bob has a 1, or Alice has a 1, Bob has a 0. So that would make A control B to be 1. So it's basically for them, if they are doing this classically, their strategy would be, let's make it 70% chance of winning. But then if you can have a quantum strategy, you can win this more than 85% of the time. So let's say that, of course, this would involve entanglement, because you will have information that is embedded in the entanglement initial state. Then you can have some correlation between your outputs. Say they have a pre-entangled qubit. They entangle their two qubits to this state. So this is arbitrary, but just without loss of generality, we can pick just this one. So we know if Alice measures a 0, Bob would definitely measure a 0. If Alice measures a 1, Bob will get a 1. And this is very helpful. Before I show you the next page, also I want to remind you that we had in a couple of classes earlier that we know that measurement is also kind of relative. Depending on what basis you use, you can get results aligned to your basis. So this is very key for this game, which I will show next. So just a reminder, you could measure things in the basis of 0 and 1, and then your output would be some probability of 0 and probability of 1. But you could also measure along a different basis. Say you can measure our quantum system in the plus and minus basis, then your output would be aligned to either plus or minus with the probability. Okay, and this is what Alice and Bob will use for their game, for their strategy. So the clever thing is that they're using both the entanglement and the fact that they can use different bases to measure things. So before they start the game, they agree Alice will measure along the z-axis, which is our the most used basis, the normal 0 and 1 basis, if the referee gives a L equals to 0. But Alice would then measure along the plus and minus basis if the referee gives 1. The thing is that if Alice measures a 0 or a plus in either basis, she would then report a 0. If she measures minus or 1, she will report a 1. Then in Bob's case, he would use this very weird different set of bases. They can be anywhere on this block sphere. And earlier I have mentioned when I introduced block sphere that usually is not that useful unless you just look at a single qubit. And turned out that is actually very useful in this game. Bob can use the block sphere and he can choose these two particular axes as his measurement basis. So the pi over 8 puts this axis 45 degrees away from the z-axis. So basically in the middle of this two normal axes that we typically would write out. And he has another option, which is perpendicular to this pi over a, is minus pi over a. So they agree. If the referee gives m equal to 0, then Bob would measure along this pi over a basis. But if referee gives m equal to 1, he will measure along this one instead. The interesting is that you can write out the exact state based on the angle. And you just write out what this state would be in terms of cosine the angle and sine the angle. And these cosine and sine are the amplitudes that you will get. You can already see from this visualization that these two states are closer to the 0 over here. And these two states are closer to the 1 over here. So Bob agrees that if he measures pi over a or minus pi over a in the m equal to 1 case, then he will report b equal to 0. If he measures either these two states based on what the referee asks, he would report b over 1. So this then can guarantee that they have a really high likelihood of getting this table right. Because interesting, so you already can see that these two are closer to 1, these two are closer to 0. So let's pick a place on this table. You should try all of these cases, but let's pick one. Like we know that this one is the hardest to guess. Let's just pick this one. So this case, Alice has L equal to 1. So then she would measure along this axis and say she gets a plus and she reports A equal to 0. So then we know that this one is the one she reports. Bob has to get a 1 in order to win this game. How would that happen? We know that because their qubits are entangled, when Alice measures a plus, Bob will measure a so Bob will measure a pi over a or minus pi over a, these two states. Because we know we're just changing the basis of the measurement. If Bob were measuring along the z-axis, he will get a 0 because Alice got a 0. Say if Alice got a 1, on her basis, she will measure a minus. So then we know Bob would definitely be measuring either these states. So we know that we're looking at this case. So m equal to 1 in this case. So Bob is definitely gonna get, not definitely, but has a really high probability of getting this state. Why? Because this amplitude cos 7 times pi over a squared is 0. How do we know this is 7 times pi over a is the angle away from the z-axis? So it's 1, 2, 3, 4, 5, 6, 7 of them. And that's why along these special states, they are 45 degrees, so they have these symmetry here. And you're maximizing Bob's chance of getting a 0 out. So I think I might have made a mistake in my talking here. So Bob has to get a 1 out. So sorry, he has to go on this state. So, on this state. So yeah, okay, sorry. So it's actually sine 3 times pi over 8 squared. That is 80%. So if Alice measures a 1, then is this case here. And Bob needs to get a 0 out. And then is along this axis. So Bob would get this state. And this is when he will report B equals to 0. To help understand this a bit more, let's just take a look at the code. So I probably just picked the hardest case to show you right now. So it might be a little hard for people to see it right away. Let's try look at this simple case, and then we're going to look at the code. So say, okay, let Alice use this normal z-axis. So when L equals to 1 case, she's going to measure either 0 and 1 along this one. So let's pick this case when Bob measures a 0. So he's going to measure along this one. We know that when Alice measures a 0, Bob will measure a pi/8 instead of the this opposite one. So on this one here, the 0 state has 85% of chance, and this is something like 14%. So he's going to be more likely to get 0, and that's what he's going to output. So this is a setup. So basically, you have this table, and you are putting your qubits in this position where it's maximizing the chance of getting the correct answer. And the chance is based on the amplitudes of these cosine and sine in front of them. You guarantee that when either case, you have a higher probability of getting 0 for these uppercase and higher probability of getting 1 in the lowercase. So let's take a look at the code that hopefully helps too. The Q# exercise we're going to use today is on the QDK sample code. We're not going to do the katas, but we do have a Chsh game, so that I will leave it to you as a piece of homework. Let's look at the sample code, and this is also I want to show you some other places you should look up for more additional tutorials. On the Microsoft Docs website, docs.microsoft.com/quantum, you'll be able to find all of the documentation about Q# and QDK and a lot of tutorials. And here in the Q# code, I don't know if people can see this. I can try to expand it, but on your own teams, you can also do Control+ or the equivalent on Mac to zoom in. So you can find on this sample page, this validating quantum mechanics with the Chsh game. So nicely, you can download it, or you can go to the browser. It's on GitHub, so you can download the code there. Depending on the IDE that you use, we have many options. You can run it on Visual Studio Code and using Python or use C#. So in my case, I like using the Visual Studio Code. And yeah, you can use it in Jupyter Notebook or whatever IDE you want. So this is the sample code. And it also gives you a nice history, some reading to do beforehand. So we're just gonna look at how this is set up. It's actually quite simple. So here it wants you to measure the Alice's cube. So Alice is gonna measure her qubit in her basis. So that's how you can set up. So measure is M, reset is resetting your qubit back to 0. So this is kind of like a just initialization step. Every time you finish, you can reset your qubits. But here reset is resetting to, let's look at the Z case, because this is a normal case. So it's called computational basis. Don't get stopped by this jargon here, but it really just means it is this axis here. So it's just doing a measurement, and then you can reset it back along this axis. And if you want to do a measurement and resets on the plus and minus axis is this one. In this case, they call it X because this is a line along the X. And they call it sign basis because plus and minus are signs. I think that's why. And in Bob's case, then it's very similar. You can set it up. Oops. And to zoom in. In Bob's case, you can set it up very similarly, but in this case, you have to rotate your positions on the block sphere. So remember, we talked about the RY rotation matrix is for any arbitrary point on the block sphere, you can change the angles. And here we're just trying to change theta, and we're trying to put it to the 45 degrees. And we see that theta over 2 is the angle that you want to get. So you have to time it by 2, pi over 8, because pi over 8 itself is 22.5. So you time it by 2 to get 45. So this is doing exactly like what Alice did, but just using the RY matrix to get to where you want. If you want to measure along the pi over 8 basis, then you will get 0. Then this is the basis that you're going to measure. So then if you want to measure along the minus pi over 8, you're going to do a rotation to this point here. So then afterwards, you can reset it back to normal, but it's not necessary now, I think. So then just after you put together the operation, you set up the strategy. And these are operation measure Bob qubit, measure Alice Bob qubit, which you use at the end here. Before that, you need to entangle their qubits. We use a H and C naught. So that's it. That's how you set up this nice algorithm to achieve this output. So what this code does is calculating your probability. So you don't quite see the output, but it's telling you the probability of running this algorithm. So on the Visual Studio Code, we use the .NET run. Okay, don't worry about the warning. Yeah, so it says classically we'll get about 75%, and quantum is 85%. So quantum success rate exceeds classical success rate. But then I also wondered, is this like do we have to put on these two particular axes? Can we change the angle a little bit? So you could. I think there are some other angles you can still get high probability to get 0 and 1. I think if I put it a little bit off, it's still going to be very similar output because you are putting the more likelihood in these angles. So cosine pi over 9 is not so different from cosine pi over 8. But if you do a really big angle, if you change it all the way down here, then it becomes ambiguous. So if you want to put a really large angle, then these numbers gonna change. So try this out at home yourself. Like I'm just exaggerating here. So yeah, all you get for the amplitude, for the probability is from the amplitude. Depending on where you set as your amplitude, you will get different probabilities. Yeah, I need to save. Yeah, so the pi over 9 cases are still like pretty high. Oh, sorry. Yeah, so that's it. That's pretty neat little algorithm. It's a nice trick that demonstrates both the entanglement and the use of measurements, and that's very useful for our understanding later on when we had a class around Groover's algorithm. And this helps with the thinking that you could do measurements on the block sphere anywhere, really, that you can just choose arbitrary basis to do your measurement. And in Groover's algorithm, you have like the amplification of amplitudes using a change of basis. So we had a class on that. We're gonna do more coding exercise on Groover's later. Yeah, so like in the pi over 50 case, it's still higher a little bit, but it's very similar. So the probability dropped a little bit. So for further reading, further learning, I came across this nice recording by Professor Ryan O'Donnell. His class on Chsh Game. So it's about an hour long. You can feel free to watch it, but I think the beginning, so the setup is the same, but he's using not the block sphere, but the collapsed 2D circle. So it's a different representation, but it's the same, telling the same story. But I think what's interesting in this lecture is later he also gives several different schema for classical strategy. So he showed that you can have many different types of classical strategies, but then still you cannot exceed 75%. So the best case scenario for classical is 75%, but the quantum boosted up to 85%. So that's interesting to see. Before we finish off, I mentioned the no cloning theorem, and I just want to quickly show this. That is so simple. The proof is so simple. I don't even have to draw a cartoon to explain it. So we can look at this step by step. So no cloning theorem is saying that we cannot copy a qubit. So that's why we can do things like teleportation, we can entangle them, we can infer measurement results, but we cannot create an exact copy of an arbitrary state. So if you had one, that would be something like an operation. So in this case, you have a function called copy. And if you have arbitrary state phi with 0, don't worry about the tensor here. It's just showing that it's putting these two qubits together. No entanglements happening here. And if you can make the 0 into phi, then you will get this case out. So you can first try to expand the right-hand side. The phi will have an arbitrary amplitude for 0 and 1, alpha and beta. And the other one also. Then you expand it, you'll get these different 4 terms. But then if you expand the left-hand side, you would 0 is still 0, but the phi is alpha 0 and beta 1. You will get this out. So then if you compare these two, they are contradicting. So that means you can't really have a function called copy to produce something like this. Is in a way, assuming that we know that in quantum operations, the gates are all unitary. So this is showing that you can't find a unitary operation that produce a copy. But this doesn't take into account measurement. So this proof is in a way not complete, but quite intuitive. You could have a more complete proof that includes measurements, which means that you would just look at each qubit. You would not just use the amplitude, but you also look at and do measurement and look at the states. But that also shows that it's impossible to have such way to either use a gate or do a measurement to get a copy out. It looks simple, the math is just very straightforward, but it is a fundamental rule in quantum computing or in quantum mechanics is fundamental because we know any arbitrary state in quantum computing can be written in this way. Because our states are linear, if you want to make a copy, you will get nonlinear results, and that's not possible. So it shows that our universe is governed in a linear way, and we can't copy information this way. And also, we cannot really delete information. So this is no cloning theorem. That's all we are discussing today. So before we go off, a reminder, on July 16th, we have the Azure Quantum Developer Workshop. Sign up. This is an opportunity for you to learn more about how you can now use quantum computing to solve your problems. We'll talk about case studies and Microsoft developing this cloud-based platform for people to write programs in Q# and be able to access hardware, quantum hardware, through the cloud. And I'm giving a talk on learning quantum and with a lot of other colleagues. And we have virtual labs to show and have you work on some problems hands-on. So this is definitely an information-packed event you should take advantage of. It's all free. So register and tune in on Thursday. Any questions you can post in the chat right now. I'm staying on for a couple minutes longer. And for any question that comes up, feel free to post on Hackaday projects. And all the recordings are on Hackaday or on YouTube channel. So that's it for today. Let's see if there's any message, comments I can answer now. Yeah, thanks so much for people who have been coming to the class, posting links. You're already very familiar with the materials we have. Yeah, so Davo, for starting, yeah, just follow the dates. I put labels on the topic, and let me see if I have that window open now. Okay. So we have all the recording links, and I label them with the topics and also the time that is recorded. So everything is in here. If you look at all 16 files, I will upload today's in a bit. So session numbers, recording, and also the topic. Yeah, thanks, David. Yeah, you may not have to do all 16. Look at the topics. There are some overlaps. So the later ones we have started coding. The earlier ones is more theoretical. It's all conceptual. Oh, Adam asked if there is a circuit editor. We intentionally did not build a circuit editor so far. And that being so, yeah, this one doesn't have circuits. So a couple of simple circuits, you can write the circuit step by step, and teleportation or superdense coding, these are very simple. But then if you want to do real quantum computing, circuits not going to get you very far. So we're not, you can learn circuits, and I know a lot of people would start learning quantum that way. But then later on, when you really start writing code, we're encouraging people to get onto the coding directly, because circuits are not going to scale. I have a nice comic somewhere about using circuits, because if you have a lot of qubits, because that's when you are actually going to make useful quantum algorithms, then circuits are not going to be very sufficient. Let's see. I had a comic for that earlier. Where can I sign up for the workshop? The link is on the aka.microsoft.ms Astro Quantum Developer Workshop. Also, I showed Visual Studio Code today. We have a hands-on tutorial step-by-step showing you how to install and download the QDK extension and start coding with Visual Studio Code. We have a Microsoft Learn module. So it's aka.ms learn QC. Straightforward. This is a module that I would recommend you go through that, and you will be able to, you can use other IDEs too, but this one is a hands-on step-by-step, as helping you set up everything, and you can run all of the samples and download the katas and run it locally. Yeah, so this was this comic showing that for simple circuits, you can write it out, but it's not gonna help you when it's getting large scale. Yeah, there are other circuit tools online, so you can definitely try them. But for serious coding, I would recommend starting to code, even when you're writing something simple. All right, thanks everyone. That's it for today. Have a good week.